Hi, y'all.
Good morning.
I got your email, Cheyenne. I just saw it. You're fine. You got it to me. We're good. Great. Now you're fine.
Thank you.
Outstanding. Let's see. Let's see. We don't need to see that. We don't need to see that. Let's look at my open math. Let's look at that. That seems like a good thing to look at. So just to make sure you are up to speed, I want to grade your quiz. If you get, I said in here, your quiz is due kind of at the end of class today because I want to, as soon as the class is over, I want to start grading it. If you give it to me tonight at like midnight, then I'm not going to get it back to you in time tomorrow. But if you still have something you're finishing up on it, fine. Like get it to me later today. It's okay if it's a little bit later. But I'm going to basically, when this class is over, I'm going to start grading stuff, and I want to be able to get it back to you ASAP. So, and it just kind of turned out, I mean, you should have been working on them a long time ago anyway, but the take-home quiz again is worthless unless I can get it as a PDF file so that I can write on it and then get it back to you, because you need to learn from it. That's the goal of it, is for you to learn from it. So I sent you an email about PDF files. I don't really care how you get it to me. You can, inside this link right here, you can link it in my open math and get it to me. You can just email it to me. But the main thing is that you either scan it on a printer or you scan it with an app on your phone, Cam Scanner, or an iPhone has a note app on it, a yellow note app. And so you can just aim at it. But the key is if you take pictures of it, it ends up grainy and too small. It's hard for me to see sometimes. Whereas if you send it to me as a PDF file, totally easy to see. And I can pull it up on my computer, write all over it, email it back to you, and then you can learn from your mistakes. So get that to me today. And then the Horizon project is also due today, which I hope you've been done with for a few days, but you still can ask me some questions after class today. I try to give you enough time that you have plenty of time to ask me whatever you want to ask me. But I'm going to grade those two things today. You'll have most likely have your quiz back later today. I'm just going to sit here and grade until I'm done with all of them. And then same with the Horizon line, but I'll start class tomorrow by answering that. And I guess in case you have only recently put time into it, it would not be weird for you to have trouble with that question. That's a legit challenging question, algebraically and with respect to calculus. And so to not completely get that would be, I don't want to say it's okay. I want to be giving you hints, but I'll answer that tomorrow. And I hope that if it hung you up, that when I solve it for you, you go, oh, I see, yeah. I can't tell you how many times I've been trying to learn something, maybe it's math related, and I think I just can't understand this, and so I sort of wimp out and watch someone do it, or cheat, look at Google search or whatever, and I see them do it, and then I think, oh man, I did know how to do that, and so cool, I still learned something. But it's kind of hard it's kind of hard to decide when to give up. Like, this is way too hard for me and I'll never get it, versus no, if I just gave you a hint, then. So the problem I have as a teacher with these kind of questions is if I don't give them interesting questions to you, then you don't realize how cool calculus is. If I do, it's going to be challenging. But I don't know if you know what Sherpas are, but Sherpas are hired to carry people up Mount Everest. It's like, yeah, I mean, it's a difficult climb, but does it count if someone else carries you and all your stuff up there and just sets you on the top of Mount Everest? So I try to give you hints because I don't want you to sit there and be totally frustrated and say, I don't know what to do. but it doesn't accomplish anything if I just answer the question for you. So I just try to strike a balance between those two things. We'll never get it right. Sometimes I'll probably tell you too much. And other times you'll feel like, you're not helping me. You're not telling me enough. Well, yeah, but I'm not going to do the problem. You got to do it. If you put a bunch of thought into it and, you get some of the credit, but not all of it. So what, it's only one assignment. It's not the end of the world. And then when I answer it, maybe you'll think, oh, okay, I see now. That's cool. And, maybe it was like, yeah, I wasn't good enough at algebra to really get that problem right on my own. Or you might think, man, yeah, I should have been able to do that. Dang it. I don't know what you'll think, but you're getting stronger. Like, even if it's hard and even if it doesn't make sense. And I'm very careful. I don't just hand out some ridiculous problem and say, good luck. I'm careful to give you something that you should be able to do, maybe with a few hints. So I got a bunch of these already from some of you. If you've already sent it to me, and it was kind of not as a PDF file, see if you can pull that off. I'll grade what you sent me. I mean, it won't be as good for you as it would have been. I'll do what I can with what you sent me. And it also helps a ton if you, as I think I said in my email this morning, it helps a ton if you can scan, like for the sake of the quiz, there's like 6 pages of it. If you send me 6 individual pages, it's really hard for me to pull that up and grade one and then put it away and then grab them all and put them someplace and then attach them all. If you can send it to me as one big document that I can just kind of cruise through, then I can grade it reasonably quick. So I'm saying that for both your sake and mine. And we're going to need to do this for tests and the number of times during this term. So maybe you don't know how to do that. See if you can figure that out with my help, looking online. Cam Scanner works really naturally. I've had lots of students figure that out and have success with Cam Scanner as an app that you can download on your phone, but it works just fine on your computer too. But the key is, can you send it to me as one document, not 6, whenever there's more than one page? See if you can figure that out. Any questions about that right now, or at the top of your head that are bugging you? Or
So if we submitted the quiz or the project as a JPEG, will we still get the feedback written on it, or is that just not something we'll have much of because it's hard?
I think so. Like, I have email on my iPad, and so if I go into email and I open up what you have, I mean, I can treat it like any other picture and zoom in and zoom out on it and look at it. I think I can still write on it. It doesn't show up as good. Actually, I'll show you what I mean really quick since I'm over here. Actually, let's try you, Cheyenne, since you sent me something. You see how much better that looks in a picture? So I don't know how she scanned this, but that basically looks like a piece of paper. I mean, it's really easy for me to see. I have all kinds of room to write over it. The picture is all shadowy. A bunch of the space is wasted. And so yeah, it's like, that's going to be easy for me to grade. And more importantly, I'm not looking for it to make it easy on me, although I guess that's nice too, but I'm more interested in I can write on it and you can learn from what I have to say. And that's what I'm most interested in. So everybody call Cheyenne. How'd you do that?
I actually did scan it, but when I saved it as a JPEG and not a PDF. So that's where I went wrong. I had to go to an online converter and then convert the JPEG to a PDF.
Did it look better? Am I wrong about that? Does it look better in that PDF form? Because I hate computers, like turning this into some ridiculous computer problem and you got to download all these apps. I want this to be simple for all of us. Does it look better as a PDF than a JPEG, or is that a 6 to the 1/2 dozen to the other? Was like,
well, because I scanned mine, I didn't see much difference between the scanned document that's saved as a JPEG and the PDF scan. I don't know what difference it would make if you took a picture and saved it as a PDF, but it probably wouldn't look as good.
I think the key is just don't take a phone picture of it and send me that phone picture. I think the JPEG version of it, I think, is no different than the PDF. So maybe I'm not even really speaking correctly. I mean, you just look at it and say, can you see this? If you can see it, then I can see it. in a sense, I don't care as long as I can pull it up and grade it and you can see it, then yeah, we got it right. I had a few people, I'm not even sure which class it was in, kind of asked me about one of the questions on the assignment. So I want to quickly do that for you just to kind of make sure you understand understand it. But also, this is kind of typical of what happens in a book. I teach it in what I consider to be a fairly straightforward way. Like when you leave my class, I hope you find yourself going, oh, that makes total sense to me. I get it. But then you do, you look at the book's version of the question and it's kind of like, oh man, I don't really get it. And there were kind of two questions in 3.5 that struck people that way. So I just want to say something about them. One of them was asking about the location for a horizontal tangent line. I think was how it said it, a horizontal tangent. And again, usually, although I don't think you had this time, usually you're given this assignment with enough time to ask me later because I don't want language to be the issue. But horizontal tangent is code for, oh, there's the tangent line and it's horizontal. And so that's really just code for 0 is the slope. So if you got all done, if you got all finished with a problem and it was like, oh, I found the slope equation. The slope equation is, and trig was harder than this, but let's say the slope equation was 2x plus 3. What you're used to doing is being told, okay, now use that. If x is like 7, then tell me what the slope is. And you go, okay, the recipe says multiply by 2, that's 14 plus 3, 17. Oh, the slope is 17. But can't you use that for something else? In other words, if the slope is 0, could you set that equal to 0 and then figure out what x would give you that? I mean, that's kind of an application, if you will, like go in both directions. Could you then solve that for x? And this is a little easier than solving a trig equation for x. I think you ended up with something more like 2 cosine of x equals 1 or something like that. I mean, I wonder, what I'm interested in is you learning to speak the language, which is why you have to be forced to think. Because if you just memorized 112, then when you got to this, you probably couldn't remember anything and didn't understand it at all. But the concept that to solve for x, I'm going to have to get rid of 2 in cosine, and that I can get rid of 2 right now. And now to get rid of cosine, you take the inverse cosine of both sides. So I take the inverse cosine of a half, and the inverse cosine of cosine gets rid of it. And so now I found the value that makes that slope equal to 1. I mean, maybe that was my question. Hey, where on this graph would the slope be 1? And so now you're using the slope equation to find the location where that would happen, if you will. And so, to look at a curve like this and say, yeah, right about there, the slope would be 1. I wonder where that is. So I know the slope is 1. Well, then set your derivative equation equal to 1 and then find the x that makes that happen. And so to me, that's speaking the language of algebra. Not, I was in algebra 6 months ago, but I actually speak the language of algebra and I can get stuff done. And so, as I said, part of this, a big chunk of this class is maybe learning your algebra better. And I'm more than happy to give you all those kind of hints when we have time. And you really need some one-on-one time with people to make sense of this, but don't settle for just, someone tell me what to do and then I'll do it. Like, make sure you're kind of go, oh yeah, that makes sense to me now. I get it. I understand. The other question that was a little weird was something like this, where you were given some equation like y equals, I don't know, 6 times the sine of x, like that's the graph. And so, and I want to take this one all the way because this is, you're taking a test over everything we've learned starting or on Wednesday. And, you don't have 3 chances and you've got to check your own work. So let's do this question on the assignment and let's check the whole thing. Let's see if we can totally do this, completely understand it. And you were asked for the equation of the line, not just the slope, but the entire equation of the line at x is pi over 6 or something like that. It was some question that was similar to that. And that's pretty daunting. That's like everything we've done rolled into one. It's very sterile, but it's all rolled into one. So you say, okay, easy. I know how to take the derivative of sine, it's cosine, and the 6 just comes along for the ride. And so again, what you have here now is sort of your slope recipe. I hate cooking. I don't know why I always use that illustration. But this is using it kind of the normal way, which is, oh, okay, great. I know what X I'm at. And so now I can know what the slope is right there. And again, the book was being nice to you by choosing pi over 6 because the cosine of pi over 6 is a nice clean answer and you don't need a calculator for it. So if you look on your unit circle at pi over 6, you know that cosine is telling you the X coordinate of that, then you say, oh, I looked on the unit circle and it's square root of 3 over 2. Now, is there any reason you can't bust out your calculator and just type the cosine of pi over 6 in radian mode? The answer is no in the real world, but because this is an online homework assignment, they said get it exactly right. So if you bust your calculator out, you're not going to get it right. Like it's got to be the square root of 3 over 2. On your calculator, when you take the cosine of pi over 6, it gives you some decimal, and you're not going to recognize that as the square root of 3 over 2. So be capable of doing it exactly right. Again, that's not fine. I mean, it's not as easy, but you still should be able to do that. So let's see, 6 divided by 2 is 3. And so I get that my slope is 3 square root 3. Cool. And of course, there's all kinds of things I could have done wrong there. I could have taken the derivative wrong. I could not know my trig and know, I could get the wrong. I could think it's a half or whatever. But be thinking as you're working on this. So let's just do this. Let's check it. Because I want you to be looking at your calculator and looking at Desmos on the test and checking your work. And so let's just go see how this is all looking. So 6 times the sine of X looks like this. And you probably don't immediately remember, but maybe on looking at this, you think, oh, that's right, that was the amplitude. That makes the sine wave taller than normal. And so we're interested in the point where X is pi over 6, which is not very satisfying. I look at this and I think I don't even know where pi over 6 is. But remember, pi is like 3 and 3 over 6 is a half. So this is like X is a half. But I can do even better. Like, why not just graph the dang thing? So if X is pi over 6, well, what would Y be? Well, it'd be 6 times the sine of pi over 6. Well, I look at the unit circle again, and sine is the Y coordinate, and the Y coordinate at pi over 6 is a half. So it's 6 times a half. So that means Y would be 3. And so there's the point. And so now I look at that and I think, yeah, that would be kind of a positive slope. And 3 square root of 3 is a weird number, but I bust my calculator out and say, what is 3 square root of 3? And it says 5.2. So it's like, yeah, that looks like a slope of 5.2. Like, I bet I didn't screw this up. That looks pretty steep. That kind of makes sense. I think I'm right. Okay. I think I'm right so far. Like, you should not need my open math to tell you you're right or wrong. And obviously you won't have that benefit on a test. So I'm not sure I'm right, but at least I got a big positive number, right, for the slope. And I now also know, because I looked at the graph, that I'm actually at, this is the point. This is kind of the point on the graph that I'm at. And so now I have everything I need to actually find the equation of the line. I know lines look like this. They've got 4 numbers to them. And thanks to all of this work that I've done, I now know that number. And at the point I'm at, that's X and that's Y. So if I plug those in, then I'm going to be able to find out what B is. There's only one thing B could be. But again, this is tougher because my open math wanted you to get this exactly right. So that means you can't wimp out, bust out your calculator and get decimals. And so if I put in Y as 3, I put in slope as 3 square root 3, I put in X as pi over 6. And then I'm trying to figure out what that B is. Well, that's not hard. You should say, I can see that this 3 would cancel with this 6 and be 2. So now I have 3 equals 2 square root 3 pi plus B. And so if I subtract that over to the other side, then I guess that'd be, so there's my B. Again, there's nothing wrong with having it as a decimal, but if you do, the my open math is going to say you're wrong. And so now I think I know the equation. It's Y equals the slope, which is 3 square root of 3 times X plus this weird B value. You don't need these parentheses, but I just want to put them in there because I found myself looking at that, being confused by it. And so again, I'm thinking, wow, that's a really weird number. But let's just think for a second. If you look back at this graph, I can't draw on this graph right now, but if there was a tangent line right there, can you see the y-intercept hitting down there around 0 somewhere? If you visualize the tangent line hitting that red point and then running down and hitting the y-axis, the B is the y-axis where it hits the y-axis, and it looks like it's in the neighborhood of 0. I can't really tell, like it's a little above 0, a little below 0. I'm not really sure. So if I did bust my calculator out just to kind of check, I'm going to type in 3 minus 2 square root 3 times pi. And when I did that, I got negative 7.8. Now I'm thinking, oh, that doesn't seem right. Like I'm a little worried now that I got it screwed up, because looking at the graph, I thought it might cross around 0. And so now I'm a little worried. Maybe I made a mistake. Maybe my mistake is an important mistake. I don't know what I'm doing. Maybe it's a dumb mistake. I wrote something down wrong. Maybe I just estimated that it would cross around 0 wrong. I don't know. I'm going to go type this in and see if it actually looks tangent. So I said that the tangent line would be 3 square root of 3 times x. Notice that x is inside the square root. I don't want the x inside the square root, so that was a mistake. I got to get outside of it. There, now it's outside. And then it was plus my b value, which I think is 3 minus 3. Was it square root 2? I have such a bad memory. Was it 2 square root 3 or 3 square root 2? I don't remember. It's 2 square root 3. 2 square root 3. And that was multiplied by pi. So sure enough, my guess was right. Like it does not cross way down here. And I will admit to you that I did this exact same thing with my class at 8 o'clock, and I got it wrong there too. And I did neither of them on purpose. And I'm really good at math. I've been doing math longer than most of you have been alive. But did you notice how that, like, the proof is now I did something wrong? That's a bummer. What did I do wrong? Well, at least now I know it. Let's go back and find it. Let's see. So I said it crossed at pi over 6 and 3. Was that really the point? Did I plug the right point in? Yeah, pi over 6 and 3, plug the right point in. And I'm truly thinking out loud because I didn't do this on purpose. Let's see, I plugged everything in.
I think when you canceled out the 6 on the bottom, I think it should be 1 over 2.
Yeah.
Not.
Yeah, isn't that a ridiculous? I mean, that's like somebody that's as good as math as me should not be making that mistake. You see this 2 right here? Is that where that 2 goes? No. Idiot. The 2 is on the bottom. Like I knew that I wrote it right there, but then did I do it up here? No, the 2 is supposed to be down here. And on a test, if you don't check your work, all I'm going to do is point at that and say, dude, on the test, because I realize that you just did something dumb too, and I won't take off as many points, at least if I can read your work. But you should not make that mistake and not know it. I should have a note that says, I got this wrong, but I don't know why. I stared at it for 10 minutes. I can't find my mistake. So let's see, that 2 is not there. It's really square root of 3 divided by 2. Let's see if that's all my mistake was. So goodbye. Divided by 2. Ah, there we go. Notice I don't need the teacher to grade it. I love notes on tests that say things like, don't even grade this, I already checked it. I love that. I mean, that's great. The idea behind math is, like, if you're going to get paid to know this, there can't be somebody checking you. Do you understand that? Like, that's why you're getting paid, because you're the one that can figure stuff out and check it. So now I know I'm right. Notice it crosses around 0 now, because that's kind of what it looked like. But more importantly, it's like perfect. It hits a tangent, really does look accurate. Oh man, I'm loving it. I'm done. It's awesome. So you should make stupid mistakes. That's just part of math. I mean, I just did 10 things. Like, I'm not going to get them all right. having said that, for me personally, as a temperament, I make a lot of dumb math mistakes because I get in too much of a hurry. I would recommend going slower because on a test, you're probably going to panic if you realize, oh my God, I got it wrong, and you don't know why. In my case, I'm good enough at math that I knew my mistake was dumb because I know what I'm doing. Like, but you're still just learning this stuff. So you'd be like, oh no, now you're all panicky and so forth. So it's better off just to go slow and write more clearly and be careful and all that. I wonder how many of you saw that mistake while I was doing it. And when you saw it, I wonder if you thought, well, I must be wrong. He's the teacher. He knows what he's doing. I wonder how many of you saw that. But my point is that's what's going to happen a lot of times in a book assignment. If I'm grading this as a teacher, I might, if I don't say you need to get it exact, I would have turned all this into decimals. I like to work with decimals. Because as I said, like this as a y-intercept doesn't really tell me much. I need to know what it is as a decimal to kind of see if it makes sense. Plus, I don't want to write all that stuff down. I mean, that's the reason I missed that is because there's so much going on. But computers can't do that. Like they can't check 90 different answers. I can check different answers and I can see, oh, this person decided to round to the 10th place and this person decided to round to the 100th. And that's not the point of what I'm teaching. So I don't care how they rounded. Good job. You got it right. Computers can't do that. They got to say something like round to the 10th place or do it exactly right. My point is you should be able to do that. But it just might look a little bit different. Hope that discussion helped a little bit, and let's launch in to the purpose, the real purpose of calculus. Anything else you need to say before we do that about either something in the assignment or you want to have something about the...
I just want to say one of the assignments wanted way too much simplification for, it was the one where there was like, you took the fourth derivative of the equation.
Yeah.
And it
wanted the one you
like,
emailed me about, Vale?
No, the one I emailed you about was one, the problem still worked fine, but it kept throwing a bunch of errors. Just even when it generated the problem, it was like a sine and cosine problem. It was just throwing errors when you generated the problem. I still answered it and got the answer right, but it was complaining.
So you're saying
but
you're saying you tried to solve it and it was like it, because again, teachers wrote these and maybe they didn't think carefully enough about how they generated MCOs. You're saying it's like it was an error before you even started, and then you said do a similar problem, and then finally it gave you one that actually made sense.
No, all of them worked. It was just well, let's see if I can open it. It just kept practice. Okay.
If you can, this I told you guys that. Go ahead, Vale.
Question 6, caught warning in the question code, a non-numeric value encountered on line 7 and file blah blah blah. Yeah, it just throws an error. The question still works. It just
got it.
Wanted to let you know.
Please send me stuff on that because, as I said, I'm saving you guys a ton of money by allowing you to buy a book online someplace that's cheaper, and then this online homework stuff is entirely free. And it's good. It's good quality, but that doesn't necessarily mean there's a question I might have assigned that isn't coded correctly or something, and I want to know that so that future students aren't screwed up and either get rid of the problem or fix it if I can get in the code and fix it. So let me know that kind of stuff, and I'll adjust accordingly. If like there's some problem that's broken, I'll go in and give everybody points on their homework and fix it. So just don't worry about that. And I apologize for that. I mean, you're saving money, but I apologize for that because it's hard enough to learn this when you're assuming that the problem's right in the assignment. We've tried to catch all that, but the problem is if we look at the question, it looks good to us and it's like great, but what if the next question it produces isn't great? It's hard for us to tell sometimes. So anyway, so if you have a screenshot of any of that, Vale, send that to me and I'll fix it. Yeah, and then I don't know, because I purposely didn't take time to talk about this, but there was that one question that asked you to find its derivative, and so it's just kind of interesting. I hope you navigated that okay, but it's like we said, oh yeah, I know how to take the derivative of sine, it's cosine, and so great. But then it said, okay, well, great, now keep going. What's the derivative of the derivative? What's the derivative of cosine? Oh, that's easy, it's minus sine. But then it said, okay, we'll keep going again. What's the derivative of minus sine? Well, remember that's like -1 multiplied by sine, and the constant just comes along for the ride. So the derivative of sine is cosine, and then there's still a -1 sitting out in front. And so keep going. Okay, keep going. 4 of them, 4 derivatives. It's the only kind of problem a math teacher would make up, right? Like, let's just take it 4 times. How about 8 times? How about 30 times? But the derivative of cosine is negative sine, but then there's a -1 out there. So it's negative sine, which means you're back to sine again. And so in a sense, that's an interesting question, because it's like if you take 4 derivatives, it's back to the sine again, like you're right back to where you started from. So does it make sense if you took 8 of them? If you took 8 of those derivatives, then you'd still be back at sine again. And notice you can't continue with that language forever. In other words, if I said 8th derivative, do you see what I did? You can't be like, take the 47th derivative, like, you know, that symbol stops being good after a while. But nobody ever does that except for weird math people. Like, you know, there is a reason to take a first and a second derivative, but it's real uncommon to have an application that goes past 2 or 3. But, you know, some math nerd just thought, oh, isn't that interesting? There's a pattern since there's a cycle. So a person could actually know the 8th and the 12th and the 14th. I'm sorry, the 8th, the 12th, and the 16th. So that's just interesting. It's worth thinking about. Anyway, hope that didn't destroy your soul. So the whole reason that somebody thought you should take this class is chapter 3.6. For that reason, I've already been alluding to this in this class. I've shown you applications. I've talked about how slope is not just slope of a line, it's rate of change. So that sterile book problem I did a second ago where we found the equation of the line that was tangent to the sine wave. I mean, that's neat. That's cool. There's a physical reality there that you found. It kind of tells you, yeah, I found the slope of that curve. And not only that, I can even draw the tangent line perfectly. I can graph and find the equation of the tangent line. There's a physical reality there. That's cool. That's worth something. But what's slope really worth? What's it really mean? 3.6, and we're spending the rest of today and tomorrow talking about this. Really, what I'm going to give you today is a much better, deeper understanding of this. And I'm going to show you harder questions than the book assigns, but I'm not assigning them. And I'm going to show you in context of a real application, like what can you really do with slope? So slope, and as I've said before, is rate of change of 2 things. And as I said, in real world, it might be something like, wow, these tomatoes in my garden are just doing terrible. I think I'll change something so that they'll do better. Well, what could I change? Well, I could add some water. Well, maybe I'll water them more. Maybe I'll water them less. Maybe I'll water them too much. But the point is I'm going to change something, and I'm going to watch to see how the tomatoes change as a result. That's a derivative. Or you say, and I'm going to add fertilizer. I'll add a little fertilizer. I'll add an ounce to this tomato, and I'll add 2 ounces to that tomato, and I'll add 3 ounces to this tomato, and I'll see like which one performs better. Like, that's what you're doing. You are changing something to see how it changes something else. Wow, my grade in this class is terrible. I think I'll change something. I think I'll work 1 more hour a week on it and see if that makes my grade go up. Like, calculus is the mathematics of change and motion in life, and slope is not just the steepness of some line that you draw in some irrelevant equation like 6 sine of x. So let me show you what I mean. So these are problems that I took directly out of our Math 96 class. And the questions that are being asked are algebra questions. This is like an algebra 2 level question. We're going to do calculus to it, but I want to give you a second to kind of understand the context of this. So we're going to ignore this over here, although I may say something about it in a minute. But this is a chart, and I wrote the Math 96 book, so I found this chart online, and I just screen captured it and cropped it out and stuck it in the book. And what this is explaining the relationship between how far you shoot your gun and how much the bullet drops. Notice the scope on this is sighted in so that at 100 yards, if you aim at the target, it'll hit the target. Now that doesn't mean the bullet isn't dropping. It just means the scope is set so that you'll actually hit what you're aiming at 100 yards. But obviously as the bullet flies through the air, the longer it flies through the air, gravity's pulling it down. And so if you make a 175-yard shot, now it's actually hitting 6 inches. And notice it doesn't say this in there, so this isn't a very good chart, but doesn't it make sense? It'd be nice if they told you what that was? Like, is that centimeters or inches? I would need to know that, wouldn't I? So basically, if you make a 175-yard shot, you're going to hit 6 inches below the target. And of course, this is not, they're not telling you this so that you can go, here's how to predict how bad you are. You're going to miss it by 6 inches. The goal would be, well, now I'll raise it 6 inches and now I'll hit the target again, right? And this is not a lesson on how guns work, but the part that I crossed out over there, if you look at that and see, I'll erase part of this. If you see that, you actually, there's a little thing on the side of a scope and you can actually make 28 clicks on it. And then you can actually just aim at the target again. And that's setting the scope to take care of the 6 inches automatically, because it's really hard to look at something and just kind of aim your gun higher and hope to hit it. Like, what is 6 inches out there? I don't know what I'm aiming at. So you don't have to guess. And so this is like for marksmen, people in a contest, or maybe a sniper in the military. So if you can get yardage, then you can actually adjust your scope and still hit your target. So it's really cool. And this is neat stuff. But of course, the relationship is kind of a duh in the sense that it's like, well, the longer you shoot, like if it's 325 yards, notice that's massive. 54 inches is like 4.5 feet. Like that is way the heck out there. And 325 yards is not that long of a shot for marksmen or people that are in contests. 54 inches, like, wow, you're going to miss your target by a mile. And so I have gun nut friends, and they've asked me about this kind of stuff because they, really into it. They want to hit the target. It's like, how does all this work? And so you may notice up here at the top, just because it's interesting, that this is a particular bullet design. 20 grains is like how much gunpowder is in it, because a higher powered bullet isn't going to drop as much because it's going to get there faster. And so, there's a whole science to like which bullets you use and all that. And you can appreciate a gun that would really be into this. Well, what I see here is as the yardage gets bigger, then the drop gets bigger. Great. But notice when that is graphed, how beautiful the pattern is. And you would maybe not be surprised by that, because isn't it physics that's controlling that? There's a very organized pattern to how this works. And so what's really cool about this graph now is if you have a really accurate graph, does it make sense you could do something the chart didn't allow you to do? Like, what if my shot was right in between 350 and 375? What if it was like 360 or something like that? Does it make sense you could go over to this graph and say, let's see how to read this? 360, 370, 380, 390, yeah, it's 10. So 360 is right there. And I can see that I'm a little under that line, which is right there. Let's see, what's this worth? 1, 2, 3, 4, 5. From 80 to 60 is 20, divided by 5 is 4. So this is 64, 68, 72, 78. So it's a hair under 78. Does it make sense? Because I have a graph, I can actually guess the in-between stuff a little bit if I wanted to. But even better, if we could find an equation. If I could find an equation where I could plug 360 into it and it would just spit out the drop, like this is what algebra is for. And I hope you already know this. Like, I'm in a sense not teaching you anything you don't know, but I'm a little worried that your teachers have not shown you anything practical like this. Most people think algebra is stupid, waste of time, and it's because it's always X's and Y's. But this is a real problem that if you could do this, then you would be worth something. You'd be making more money, or you'd be winning more contests in this context. I said in this problem to these Algebra 2 students, use regression to find a quadratic equation to model this. So can you go from the data to the graph and now ultimately to the equation? And I said quadratic because they aren't as good as you. You should be able to look at this graph and say, yeah, parabolas look like that. The question is, do you know what regression is? You should, but maybe your teacher didn't do their job. So we're gonna do this together really quick for this first one. Let's see, let's pick a few of these points. Like, let's pick 150, I don't know, 225, 300, and 375. So I'm going to do this with you. but we're going to pick those 4 ordered pairs because it'll just save us some time. We won't get as good of a graph. We won't get as good of an equation as we would have if we put them all in there. But I'm just going to show you how to, on your graphing calculator, to do regression, which means regression is the name assigned to how do you go from ordered pairs to an equation. So then I got rid of those, and so you're wishing I hadn't, but I'll type them in again for you in just a second. So I'm pulling up a calculator over here. So can everybody see that calculator now, just to make sure I'm doing my job here? Tell me if you can't.
Yeah.
Thank you. So if you go to stat, I just went to stat, there's 2 main options. You can edit or calculate. Again, maybe I'm telling you something you already know. I hope I am. I'm going to go down to clear list because maybe I have numbers in there from before. And I'm going to say clear list, and it says, okay, what do you want to clear? And I'm going to have numbers in list 1, comma, and second list 2. So it says, okay, I'm done. So that if I go to stat and I do what I want to do, which is edit this, I want to stay on edit. What I'd like is for there to be nothing in here, like there's no data in there. You can just type over the top of your old data, but I just wanted to get rid of mine. So now I'm going to go put those numbers in. And so let's see, the ones we chose were 150, and we chose X is 225. Do this with me too, and ask me questions if you've never done this before. If you've done it, then I'm just going to waste a few minutes and come up with an equation, and you already know how to do it. But my opinion is if you can't do this, this is the whole point of algebra. Like you sat through all these algebra classes and you can't even do anything interesting with it. That's shame on us for not doing a good job teaching you. Is kind of the way I look at that. And let's see, at 150, it dropped 3.2 inches. And at 225, it dropped 15.3 inches. And at 300, it dropped 41.7 inches. And finally, at 375, it dropped 84.9 inches. And I'm not going to take the time to do this, but I could hit graph and you would be able to see those points, but I'm not adjusting the window. And of course, I don't see them now because notice the window is not set out to the big numbers, the big X's like 225 and 300 and so forth. So I'm just going to cut to the chase and answer the question. So now if I go back to stat, this time instead of staying on edit, I'm going to go over to calculate. And this is where all the regression features live. The first one you come to right there is linear regression. Well, based on the graph I just showed you with the curve in it, it'd be dumb to find a line for this, right? Because it's not a line. And these students didn't know that. You would, but they didn't know this. And so I said use quadratic regression. And so I say enter and it's blinking because there's different lists there. So mine is in list 1 and list 2. So I can just say enter again and it says, bam, there you go. There's your parabola. There's the parabola that goes through those 4 points. And so all of that was just interesting. So great, I found the equation now. So I'm going to write that down and then we'll go do some things with it here in just a second. So before I get rid of that screen. And I said here, round it to 4 decimal places. And notice why I said that, because look at the A value of that parabola. It's so tiny that if you don't round it a long ways out, then you won't get a very good graph. So that'd be 0.0014 x squared, and then 0.3637 minus 0.3637x, and then plus, I don't have to round the last one, 26.775. So it'd be, I'm not going to take the time to do this, even though I kind of want to, but it'd be very instructive, if you will, to go graph that parabola and sort of see if it was working, see if everything was kind of looking correct. But I'm just going to assume I didn't blow it. So I found the equation to model this. And do you understand what the power that gives me? And this is what I was teaching the algebra students and why I wrote this book. Look at that second question right there. Again, I'm just saying this rhetorically, like, is this something you could do because of the algebra you took? So notice I said, use your equation to predict the drop for a 170-yard shot. Well, you can see why I said that, because 170 is not on the list. It's like between those two. So the best I could do with the chart is say it's somewhere between 3.2 and 6.1. And of course, I would say closer to 6.1 because 170 is closer to 175. I could go over here to the graph and go to 170 and I could make a decent estimate, but isn't it way better to recognize that, hey, it's a 170-yard shot. Oh, yard shot. That's code for X. You're telling me X is 170 and then predict the drop. In other words, find the drop. You're asking me to figure out Y. Well, isn't that what that Y equals equation is designed to do? To plug in X as an input of 170 and then have it spit out the answer. And so now I'm going to get a really accurate answer for the drop. And I don't have to guess. I don't have to guess off the chart. I don't have to estimate off the graph. I'm going to get it really good now, and I'm going to sort of win the contest. What about the second one? It says do the opposite. Use your equation to estimate the yardage. Estimate the yardage, isn't that X? If the shot drops 140 inches. And so notice, if you shot, and this is what's kind of just fascinating, is it's like if you just shot at a target and you measured how much it dropped, you could actually work backwards and figure out how long that shot was. But notice 140 is off the chart. Like 103 is the biggest one we have. And so if you're out here at 140 inches for the drop, that must be like a, what, 600-yard shot, 500-yard shot? I mean, it's off the chart. Like the graph won't even allow me to even make a guess at this. It's outside of the data. And so isn't that what algebra is for? Like, that's why having the equation's cool. You have every answer stored inside an equation. But of course, that's pretty daunting. Do you recognize that that is saying you're taking 140 and then plugging it in for Y and ask to solve for X? Hey, that's a quadratic formula. You should say, to solve that, I've got to do the quadratic formula with a bunch of decimals. So I dang well better know the quadratic formula and be able to type that in and so forth. That's a cool problem. I mean, I'd be willing to bet that 1 out of 20 students that graduates all the way through every algebra class, even though this is algebra 2, even if they went on to pre-calculus, like couldn't do something like this. I bet you, many of you think that, like, wow, I never really thought that deeply, but like this is where like math actually gets useful. It's kind of fun. But like those are all just algebra problems. What I'm interested in today, for your sake, now that we have this equation up here, is what does calculus? Why would you go one step further with a class like you're taking and do calculus to this? Like, what good would that do you in this real in this real environment? What is it we're doing every single question, or from now on in this class? What are we always doing? You tell me, what are we doing?
Finding slope.
Slope, finding a derivative, taking a derivative, which is code for slope, right? We're finding slope. So the question is, in this context, what does the slope tell you? Because it's no longer just rise over run. That's kind of the key here. The problem I just did with 6 times the sine of X, that was rise over run, and it was a literal slope of a line. But here slope means something. And that's why there's a chapter called slope as a rate of change. Like, what are we talking about changing here? Like, why, if I went and found the slope? Now, I'm just going to give you a second to think about that, but you have this equation up here, so couldn't you find its derivative now? Notice that equation is in your wheelhouse. Like, it's not an equation you can't do. You know the shortcut for finding the slope of that equation. So find that, and then go one step further and find the slope specifically at, say, 200. And what I want to know is, can you understand what you found? You're going to get a number out of that, but my question is, do you understand what that number means? In my opinion, if you get an A in this calculus class and you can't do that, then you can't do anything. Like, you can't do anything in the real world. You're worthless, if you will, with respect to using this to do something. So let's see if we can learn something a little more deep about what slope can tell us. That's the idea here. I'm going to give you a second to see if you can get the right numerical answer for that. Can you still read all that up there, or did I make a mess of it? Super easy derivative to take because it's just power rule. But notice you don't have nice sterile numbers like you do in a math book. You have all these weird decimals. Like the real world is decimals. Very seldom is it whole numbers. There is a decimal point in front of that 0. It was covered up.
Aren't we finding the instantaneous rate of change at that point?
Yeah, that's exactly what you're doing. You're finding not so much the slope, but the instantaneous rate of change. And so the question is like, what does that mean in terms of units here? You're exactly right, Caesar, but you got to add units to actually see what does that tell me about. I'm making this 200-yard shot, and I'm talking about data that's like yards of shot and inches of drop. And so what does instantaneous rate of change mean in this context? So I'm going to catch up to you. Let's see if you, power rule says multiply the 0.0014 times 2. So that'd be 0.0028. And then the derivative of constant times x is just the constant. So that'd be 0.3637. So there's my slope equation. But then I'm analyzing this when x is 200. So, okay, got my calculator out, 0.0028 times 200 minus 0.3637. Double check that I typed it in right. I got like 0.196. I'm just going to round that off to 0.2. So everything I've taught you so far, you should be able to get 0.2 without too much trouble. Yeah, I got 0.2. Question correct up to now. But today, and again, this is harder than what the assignment is. Today, it's like, what does that mean? Well, remember slope is change of y over change of x, right? It's a fraction. 0.2 is a fraction. Now you could think of it as 0.2 is 2/10 or 1/5, or you could just put it over the top of 1. But you got to make a fraction out of it in order to make any sense of this, for one. And then the second thing is you got to get the units back involved.
It's inches per yard, isn't it?
Yeah, notice it's change of y. What are the y units? The y units were inches of drop, and the x units were yards. I guess I'll just leave it at yards, but I could say shot yards or yard shot or something like that. Does that help you at all? Does that mean anything to you now? Would you get the units back involved? It's even better if you go in and put plus signs. Go ahead, Cheyenne.
So if, say that 200-yard line, say that was just like a force field or something, and the bullet hit that, would that 0.2, is that how fast it would be dropping if it didn't move any further in the x direction? Would it be 0.2 inches? Like if it just went like this and then just straight down, that's how fast it would be dropping if it didn't move any further.
Well, the key is to this, to really understand it, is it's not always speed. Like rate of change is often speed. That's a great application of it, but in this case, it has nothing to do with speed, because notice there's nothing about time in any of this stuff. And so, like you, Cheyenne, it's like I want to get speed involved somehow, but there is no units of speed here. So notice that the 200-yard shot up here, I am predicting a 10.2 inch drop. Like it's going to hit 10.2 inches below the target unless I do something about it, right? Well, what is this saying? And this is where the plus signs are really good, because if you add those to it, you don't say plus in the real world, you say increase. Like plus is increase, negative is decrease. What this is saying is if you increase your shot by 1 yard, so you go from 200 to 201, then it'll increase the drop by 0.2 inches. So in other words, it allows me to jump to the next length. And so it's like, oh, I got a 200-yard shot. Well, then apparently it's going to drop 10.4 instead of 10.2. It got 2.2 inches more of a drop. It's telling you about the rate of change, but what are the units? You see what I'm saying? Like, this is really cool stuff. It's really powerful, but it's not a slope. Like, this has nothing to do with some line you draw. It has to do with the units that are involved. And every problem has different units. And there's just a ton of applications to that. Again, as I said, it's like, oh, my tomatoes terrible. It's not growing at all. It's only 3 inches in diameter. I think I'll add 2 ounces of fertilizer and see how much it grows in a week. See how many inches per week of diameter change I get in that. And so, you know, that's the idea here. I'm trying to see how it's changing. But here's something surprising. What if you went back and said, well, what about, you know, I don't know, let's go out to 400 yards. What if I'm out at 400 yards and notice out there it's supposed to drop 103 inches? And so is it also 0.2? Is it going to change by, is the rate of change out there also 0.2? Well, let's go figure it out and see. 0.0028, I don't need to write all that in again. Just plug in 400 instead, right? So I'm going to just bust out my calculator in the interest of time and change the 200 to 400, and I got 0.756. So actually, just to round it off, more like 0.8. I got 0.8. Whoa, 0.8. Really? An increase of 0.8 inches of drop for every increase of 1 yard shot? Wow, so if I change by a yard out there, I actually get 4 times the amount of drop, almost a whole more inch. So if I went from 400 to 401, it's going to drop almost an inch more. So the rate of change out there is much faster. Maybe you can picture the bullet when it first goes out of the gun is pretty much kind of staying level, right? But at some point it's like falling straight down. I mean, it's going down really fast because it kind of ran out of juice and it's dropping. And so that's why calculus is kind of cool, because the rate of change isn't the same depending on where you are. It matters where you are. Now, when I look back at the graph, don't you find yourself, because there is a, you know, you can draw this line, like, isn't that the slope at 200? And if I go to 400, isn't the slope steeper up there? Like, it's not that the slope isn't still visible. It's just that I'm interested in the meaning of the slope now, not just what's the rise over the run. All you got to do is add units back into it and think plus and minus, and you can put it into words, and all of a sudden the rate of change here is really interesting. I'm changing the length of my shot, and so I'm wondering how much is the drop going to change. That's pretty cool. That's pretty useful. You can appreciate somebody that was a marksman or a sniper would that'd be a cool thing to add to what they already understood. I would say 90% of it is contained in the algebra problem, but calculus just kind of adds one more cool thing that it's interesting to know. Anything you want to ask about that? Do you get what I mean when I say if you left this class being able to find the derivative of tangent? Like, who cares? Who cares what the derivative of tangent is? Nobody. But like, can you do something with it? Can you actually apply it to something? Notice this is a very real problem, because there was no equation here. All you had some data. Can you appreciate that you could go to the range and actually shoot a gun and measure all this data yourself? You even collected your own data, and you graphed it, and you found an equation to model it, and you drew conclusions where you could predict the future. Now you could shoot further and actually predict what was going to happen without even taking any more shots. I mean, it's just really cool what can be done with algebra. When you find there's a relationship between two things, then algebra has the ability to kind of capture that in some, you know, cool little formula. But you got to be able to speak the language. I mean, that's a big jump. I mean, I left college with a math degree, and I would say I couldn't do what I just showed you. I wasn't taught anything that applied it or made me think or helped me understand what the heck I was really doing. I got 3 of these questions I want to look at. So here's another one. water heaters. So let's stare at this a little bit. And again, water heater, what does that have to do with anything? But can you imagine there's probably people making their money designing and building these things? I mean, that's why you're taking this, so that you could be an engineer and actually build something that's worth money. So let's see if we can understand this. Again, I stole this chart directly off the internet and I thought, wow, that's really cool. So let me explain a little bit. So you have this water heater. Now, for most of your houses, you have a tank full of hot water. And if your sister gets in the shower before you and they burn all the hot water up, then you get a cold one. But tankless water heaters, which is what this is a tankless water heater. These are extremely cool because it's kind of like the water from the street goes into this tank, and think of there as being like fire in there. And so the water goes into the tank and there's so much fire in there, but by the time it comes out the other side, it's warm. And so those are really cool because you're not wasting hot water. Like right now you have water sitting there that's hot, but you're not using it. So you're heating up something that's going to waste and it runs out. Well, tankless water heaters are really cool. But take a look at this chart. So I'm saying specifically, we're going to look at one of the models that this chart pertains to, and that's this one. So in a sense, we're ignoring all the rest of this stuff, which helps because I'm confused by piles of numbers. Ignore all the rest of that stuff. What is this saying then? If you look at that, this is saying temperature rise. This is your X. The temperature rise is 30 degrees. If you do that, then this tankless water heater will put out 11.1 gallons per minute. So you know what a gallon of milk is. It takes a minute to produce that gallon of water if you want to heat it up 30 degrees. And why would you want to do that? Well, it comes off the street and it's 60 and you'd like it to be 90 before you stood in the shower. And so like, I got to heat it up 30 degrees. And so if you do that, it'll put out 11.1 gallons a minute. But if you need it to heat up 50 degrees, like it's only 40 degrees when it comes out of the street and you still want it to be 90, so now you got to heat up 50 degrees, then it only puts out 7.4. Does that make sense why it would be going down? Like, yeah, you got to heat it up more, right? So it can't put it out as fast. And so as the temperature goes up, the production of this goes down, right? That's kind of true for all kinds of things, right? If you're working and you're asked to do more, then you're going to get less. If you ask me to do more things, then it's going to take me, and I'm going to be less productive over time because I'm being asked to do more things. So again, whatever, data, you got some data here, but the important thing is temperature rise. So that's a temperature. These are temperatures: 30 degrees Fahrenheit, 30 degrees, 35 degrees Fahrenheit, 40 degrees Fahrenheit. And what are the units of the output? Well, that's gallons per minute. So there's your 2 units. Again, interesting units, really unusual units. But you can appreciate somebody designing something that would do a particular job here for a factory or for our household. Now, again, what's cool, and I'm saving us some time here, lots of time, is one is when you graph this, notice there's a pattern to it, but look carefully. Notice it's not perfect. Like, look at this first one over here. It's like almost like off the chart, sort of. And then notice the line doesn't hit it perfectly here either. Like, this is the real world. This is not a perfect match. It's close, it's decent. And to save time, I already went into regression and I found the equation for you that fit it the best. And there it is in all of its glory. Let's see, X and Y. Y is gallons per minute. So what gallons per minute is the output and X is the temperature. So this means, for instance, now that I own this equation, and we won't do the algebra problems, but this means that if I, for some reason, wanted to know what the answer to 110 was, then I could throw 110 in there for X, and it would spit out the Y. And notice based on the pattern, 4.1, 3.9, 3.7, I'd guess it's going to be 3.6 or 3.5 or something like that. And I could throw one, I could use the algebra equation to predict something that the chart didn't say. Or the other way around, I could say, well, I really need it to produce, say, 6. I need it to produce 6 gallons a minute. And so, I can see that must be between 60 and 65, but that would be like, let's throw 6 in for Y. Could you still solve that for X? Do you still have the algebra skill to solve for X? Like, that's speaking the language of algebra. But again, we already know that. We're not talking about that. We're talking about calculus. What does calculus add to this discussion? And so let's see if we can do that. So first, I'll give you a second to do this, and I want to see if what I just showed you a second ago, see if you could apply it here. So first of all, what's the derivative of this? Notice that's just the power equation. That's not a hard derivative to take. I could have found a logarithm equation and then you wouldn't know how to take its derivative yet. That's why we still got stuff to do in this class. But take that derivative and then let's use it for two different things. Let's find y prime, I don't know, early on, like at 32 degrees. And then let's find it later on, like at, I don't know, 92 degrees or something like that. Can you find those? That's 3.1 through 3.5. Can you explain them? That's 3.6. Can you explain what you just found? Can you see that that's actually something that calculus adds to this that's kind of cool? I'll give you a second.
Is that a 32 on the first derivative?
Yep, that's 32. Looks worse. So it's amazing we have a shortcut for this. Please don't forget that. The shortcut makes the derivative actually pretty easy to take because of the power rule. But if we had to do the old x plus h minus f of x thing, whew, these are really crazy decimals. Books only give you sterile problems, they never give you real problems like this. Double check your derivative just so you're not wasting time. Maybe we all round it a little differently. I'm going to say 0.63. And you got to be really careful. So you multiply the 0.95 down or 965 down to the coefficient, which changes it both to 308 and also makes it negative. But then what do you have to do to the exponent according to the power rule?
Subtract 1.
Subtract 1, and that'd be really easy to screw up here. Negative 0.9 minus 1 is negative 1.9. It's not 0.03. So now you'd have negative 1.965 for its exponent. So there's your slope finder. There's your slope recipe. And now you can throw 32 and 92 in there. And the question is, do you know what you just found? I don't care about rounding. If you round it differently, then leave yours alone. It's fine. The slope depends on your location. The second one, I only got negative 0.04. Way different, like 8 times smaller. Notice this slope came out negative. Of course it did. Look at the graph. Of course it came out negative. Duh, I knew that. But can you add the units and explain actually what that's telling you? My thought would be maybe at this point, but what I want to get across is if you can't, you're missing the entire point of calculus. We're sitting here for week after week after week trying to learn this. If you want to really use this and get paid for it, this is where it comes into play. Well, as I said, what do you have to do? Well, you have to make it a fraction because the slope takes 2 numbers to make a fraction. That's the easiest way to do it. And then I look back at the units. Well, the top was y, change of y over change of x. Oh, that's gallons per minute. So this is gallons per minute on the top. And then down here, oh, that's temperature in degrees. So that's actually 1 degree. And again, it's maybe important to notice that, hey, the bottom one's actually positive. Perhaps you could put it into words now. What this is saying is if you increase the temperature by 1 degree, in other words, you want to bring it up 1 degree more, then you're going to lose about 1/3 of a gallon a minute. Does that make sense? Notice which one I said first, because it's kind of it's causal. One causes the other. So, I'm sitting here at, well, we said 32 degrees. We're sitting here at 32 degrees, so we're kind of between these two numbers. And I say, I'd like to increase that by 1, like take it up to 33. Well, what's that going to do? How much is that going to trash my production or of my water here? Like, how much is that going to screw it up? How much is that going to take away? Oh, if you want to increase it by 1 degree, you're only going to lose 1/3 of a gallon a minute. Okay, well, let's go ahead and increase it 1 degree. And that's the idea. All you got to do is put the units back into it. But notice out here, same thing, it's still over 1. Why would that be so much smaller? Well, 92 degrees is already a lot to increase the water. And so if you only increase it 1 more degree, I mean, what's $1 more? If you need $92 and someone says, oh, I'm sorry, you need 93, well, whatever, I still need a lot of money, it's about the same. Notice you hardly lose anything out there. If you need to go up 1 more degree, pretty much the same. And that would be your answer if you were explaining to somebody on the phone or about what your system, how your system worked, to be like, it'll be pretty much the same production out there. And isn't that what the data says? Like, look how much it dropped. It only went down 0.2 from 90 to 95. It went down 0.2. You're seeing calculus right there. You don't even have to do calculus to see what the average rate of change is from 90 to 95. So that's actually it's 5 gallons per minute change in 0.2 degrees. Like, I'm seeing slope right there. I don't have to even do calculus to kind of see an average. Remember, calculus is just perfect. No, I said that right. Have I been saying this wrong the whole time? No. No, that's right.
So then to find the temperature where the water heater can't put out any more water, or where your gallons per minute decreases to 0, you would just set that derivative equal to 0, right?
Yeah, that's exactly right. And it will never get there in this case, because this equation is going to get flatter and flatter, but it'll never completely flatten out. But already we're at a place where it's close enough, right? 0.04 is already close enough. So I did say one thing backwards here because I wrote the numbers in the wrong spot. I put X on top and X isn't on top. So this is like the averages. An increase of 5 degrees represents a decrease because it went from 4.1 down to 3.9 of 0.2 gallons per minute. So we saw it was pretty small out there. Whereas early on, notice it's pretty big. It went from 10.6 all the way down to 9.3. Well, that's 1.3. That's a big change. 5 degrees there made a lot more of a difference than 5 degrees apparently made later on. Like, that's what derivatives are telling you. So let's look at one more really quickly, because I want to give you as much chance as I possibly can to understand this. This is also, let me give you a little bit of understanding of this. So this is something I look at, not because I'm a math teacher, but because I'm a kayaker. I'm constantly watching river levels. And this particular one is data that I collected because I was going to launch out here at, well, we'll say, I don't know, let's say it's a week later, day 25. So I was collecting data off the internet. May 8th, this was the river level. May 12th, that's the river level. I graphed it and I noticed, hey, look at that cool pattern. And again, it might make sense to you that physics would be in play here. In May, when it sort of stops raining, rivers tend to, all the snow melt stops and all the water comes out of the ground. And so it starts to kind of decrease. And so notice it's kind of the same shape as the last one. It was like this decreasing curve. And so it made sense to find another power equation to model it. But my real curiosity was just, I wonder what the water flow is going to be out on day 25. Notice I can answer that now. since Y is the river level, I'll tell you what CFS means in a minute, and X is the day in May, then I'm basically taking 25. This is me doing algebra. I'm taking 25, sticking it into that equation. So I'm trying to find Y of 25. And I'm saying, hey, I wonder what that flow is. Notice I could kind of guess from this graph, but who wants to guess when you can do, get it accurate? So I'm plugging that in, saying times 25 raised to the, again, weird that it's such an interesting number. The exponent is such an interesting number. When I did that, I got 185. I got approximately 185. I don't even have to understand river level. It just says up there that the unit is CFS. So I'm doing this because then I can tell my buddies who I'm going with, hey, when we launch in a week, the river level is going to be about 185. And that can either be like, oh, that's too low, we can't go, or oh, that's too high, we're going to die. But I'm trying to predict the future. Like, I'm not doing math because I'm a math teacher. I'm doing math because I'm making money at it, or I'm doing something interesting. Like, this is what algebra is really for. I went from ordered pairs to the graph and said, hey, I know what kind of equations are curved like that. Those are power equations. And I went and found, I did regression to find a power equation to model it, and I used it to predict the future. What I want you to tell me is, what is Y prime of 25, and why is that extremely cool for me to know as well? What is that telling me about the launch date? Of May 25th. I'm going to pick on one of you to answer this, so have an answer. From my perspective, there's like 3 of you face to face that I see. The rest of you are just black screens. You're like at the refrigerator right now, for all I know. Or you're in your pajamas and you just don't want to show up. Again, I'm assuming everything that you're doing here is easy because of what you've done in 3.1 through 3.5, except explaining what you just found. You just check to see if you got the same thing. I got approximately -9. I'll just round it off. Close enough. Like, I don't need all the decimals. I got around -9. So did you get -9? Good job. If you didn't, ask me a question. And not everybody did. Like, you either push buttons wrong. There's no way a class this size, every single person gets this right, even if you know what you're doing. But power rule is take this exponent, multiply by that number, and then subtract 1 from -1.2. So now you should have -2.2 for your exponent.
Isn't this just saying that on the 25th of May, the river level is dropping by -8.9, whatever that unit is, per day?
What do you think about that, Jerry? Do you think he's right? Vale says on the 25th, what that 9 tells me is that the river level is dropping -9, whatever CFS is, per day.
I think so.
You guys are right. Again, look at the units. It's 9/1. 9 is the Y values. That's CFS. Even if I don't know what it means, I can just write it in there. And then May is days. Like, this is day. And so this is a positive and the 9 came out a negative. And so that's exactly what it means. So what this tells me if I'm a kayaker is I can expect it to be 185, but I also know it's still changing, right? And it's changing constantly. And so what this tells me is what it'll be tomorrow. Does that make sense? That's what's really cool. It tells me that then it's changing, but it's dropping. That's why the negative is so important. It's dropping 9 per day. So that means tomorrow it's going to be like 175, 176. Does that make sense? So not only do I know what to expect when I put on, but I kind of know the trend. I know what's happening. And I'm doing this every year. I try to run the Illinois River and it's snow melt and just a beautiful river. And we camp 2 days out there and camp out of our kayaks. And it's just the coolest trip ever. And I do this calculation for all the other people in my group, and they of course are happy that I did it. And also like, you're a nerd. But it's predictive. That's the idea. Just quickly so you understand it, and then I'll shut up. A cubic foot per second. There's a cubic foot, 12 inches by 12 inches by 12 inches. Cubic feet per second means, so let's see, we found it up here, 185 cubic feet per second. That means 185 blocks of water that size passed by you in 1 second. That's how river flow is measured. It's a volume of cubes in 1 second. Now, for all of us, for kayakers, it's not like they think about that. They just know that, oh yeah, that's high for this river level, or that's low, and that's all they know. The particular river that I'm talking about is 200 is kind of the lowest, and so if it was 185, it'd be like, oh, this is going to be close. It's not like anybody has to do the math. It's just like, yeah, there's going to be a lot of rocks sticking up, and it's going to be kind of shallow. But notice the units are really interesting because cubic feet per second literally means cubic feet per second. But then this slope here is per day on top of that. Like, do you see how weird this can be sometimes? Cubic feet per second per day. But actually that actually makes sense. It's dropping 3 cubic feet per second in 1 day. So you can just have really unusual units. You will not see questions like this in your assignment because this is asking a lot. But if you're actually going to use this for something, you got to be able to think about this a little bit deeper. So tomorrow we're going to just narrow this down to some book questions, and we'll be talking about speed a lot. And this was a speed question because day was time. So a lot of times the unit on the bottom, a lot of times that unit is time. Those are the units kind of make more sense to us, if you will, than like hot water heater problems and stuff like that. But I guess I just want to reiterate one more time, like if you don't understand this, then you're taking this class for nothing. I mean, they'll let you be a veterinarian, but it's like you're not going to get anything out of this class if you can't understand what slope really means. So it's kind of a cool topic. All right, let's get out of here. Stay after if any of those questions are bugging you and you have others, or if you want to ask me any questions about the quiz that you're about to owe me or the project that you are also about to owe me. I've gotten submissions and I'm basically going to hang up here and start grading all that stuff and emailing you back. So this is your last shot to ask me anything you want to ask me.
See you tomorrow.
See you tomorrow, Cheyenne.
Bye all.
See you, Jesse. Have a good day.
You too.